Okay, well, now my name's Nigel Peake. I'm the head of DAMT, and it's a great pleasure for me to be able to welcome you here for this, the 12th Andrew Chamblin Memorial Lecture. So just a few words first about Andrew Chamblin, and then a few words about today's speaker. So Andrew was born in 1969 in Lubbock, Texas, and after a brilliant physics undergraduate career at Rice University, he studied twistor theory in Oxford under Roger Penrose for a year, before coming to DAMT, to Cambridge and St John's College for his PhD supervised by Stephen Hawking and Gary Gibbons. And he completed his thesis entitled Aspects of Topology in Theoretical and Quantum Gravity. After that, he held a prestigious Draper's Research Fellowship at Pembroke, and following a series of other research positions in the UK and the US, he became assistant professor at the University of Louisville in the States. So Andrew died suddenly and unexpectedly on the 6th of February 2006 at the tragically young age of 36 and at the height of his academic powers. His family and friends and colleagues from all over the world came together to raise the funding for this annual lectureship and together with an organ recital in Oxford to honour Andrew's memory. So DAMT is hugely proud of Andrew and all he achieved, and it's a great delight for us to be able to hold this occasion every year. We've always been able to attract one of the world's leading theoretical physicists to deliver the lecture, and of course that's especially true this year. So just a couple of words about Gerard Top. Sorry for the pronunciation. Gerard has spent most of his career at the University of Utrecht, where he's now a distinguished professor. He's famed for his seminal work on gauge theory, black holes, quantum gravity, and he's won a huge range of awards and accolades, including the 1999 Nobel Prize in Physics, which he shared with Veltman for their work on quantum structure of electroweak interactions. And he's in the news today because he's one of the signatories of the letter from the Nobel laureates and the Fields medalists to the UK government and the EU calling for the closest possible cooperation in science after Brexit. So it's a huge pleasure to have you here. Thank you very much indeed for coming, and we're really looking forward to your lecture.
Thank you very much, Nigel, for your very kind introduction. It is with pleasure that I'm returning back to Cambridge. I've been in this town several times before, usually to the Newton Institute, to see my great friend and discussion partner, Stephen Hawking, of course. And now I think this is a very interesting and sympathetic effort has been made to remember someone who has made his career here, Andrew Chamblin. And although I didn't know him well, I quite appreciate the fact that he's being honored as a former member in this town as a scientist. And I'm quite happy to deliver this particular lecture now. So my lecture is about black holes. Now, all direct evidence for black holes is for the very large ones, the astronomically sized black holes, ranging from mass of maybe 5 or 10 solar masses at least, to thousands, millions, or even billions of solar masses. So these are the very large black holes. And normally it is assumed that something is so large and so massive and solid that quantum effects are totally invisible in such a thing. The quantum effects may be indirect. When quantum particles enter, they might do something quantum mechanical, but not very striking and not very interesting. So, however, there is one very fundamental feature of black holes that you have to remember, which is there are solutions to Einstein's equations, but the Einstein equations do not give you a lower limit on their size or their mass. So black holes can be 10 solar masses, yes, but they could have been 1 solar mass, 1 Earth mass, or much, much lighter than that. And then the question is, okay, quantum mechanics was ignored for the very large and heavy black holes. What about these very light ones? In principle, we expect, for various physical reasons, that the lightest black hole will be somewhere around the Planck mass, which is about 22 micrograms, or the Planck size is just 10 to the minus 33 centimeters. Now, 10 to the minus 33 centimeters doesn't sound like much, and so many people say, okay, well, we have all sorts of interesting experiments in elementary particles about that range. But wait a minute, it's not about that range. Elementary particles are much, much bigger than 10 to the minus 33 centimeters. It's a very outrageously tiny distance, even for particle physicists. So, but this is the domain where probably the lightest black holes exist. And in that domain, the laws of quantum mechanics will definitely become very important. They might become dominant. And then the question is, how do black holes behave in that domain? And now, one answer I can give directly without much imagination needed. Black holes are weird things. The craziest things happen at the horizon. Time stands still. You go through the horizon. In a sense, time may go backward. So very strange things indeed. And on the other hand, quantum mechanics is also very strange. Quantum mechanics has it that certain properties of particles cannot be measured at the same time. You cannot establish the position of a particle and its momentum or its velocity simultaneously. But if you have two entangled particles, the rules become different again, and then you can measure one particle and measure the other particles and do something which you had thought to be impossible. So strange situations indeed happen also in quantum physics. So now you imagine what kind of strange things happen if you combine quantum mechanics with the physics of a black hole, the quantum black hole. Now, that seems to be the ultimate challenge, or one of the ultimate challenges of theoretical physicists. This is the most complicated problem that many of us will have encountered in our lives. Apart from solving the whole thing, because you can also think of, well, quantum gravity is still also wide open, waiting for some smart person to have the right input to complete the theory of quantum gravity. That hasn't happened yet. But I think these other questions about black holes, in particular the problem of very tiny black holes, is the next best thing. Okay, we don't solve quantum gravity entirely, but we solve it for that particular case. And that would be extremely important. And the reason why I think this is so important is basically twofold. One is it is a missing ingredient, a black spot in our theories. So of course we want to fill in our black spots with some decent looking equations. But most importantly, whatever you try seems to be in conflict with what else we know about particle physics, about quantum physics, and so on. So black holes seem to be misbehaving. And this misbehavior is even better something to study very carefully. Certainly if you have many talented theoretical physicists are devoting their lives now in trying to figure out how this black hole should be filled, literally, because this might give us new information, not only about black holes, not only about quantum mechanics, not only about general relativity, but about a whole lot together. Maybe black holes will give us important new clues about quantum gravity. And this is the deeper motivation why we're also very much interested in getting any problems with quantum black holes fixed. Or perhaps not fixed in a unique way, because we don't know what happens for the very tiny black holes. But maybe we can come with a number of alternative and reasonable theories and solutions. This is how a good quantum theory should look, and this is how it should function for a black hole. In particular, you saw the word observer in my title. The question I'm going to ask is, how do different observers experience the existence of a black hole? Because many of you have seen or even worked on the string theory approach to black holes, but very often string theorists have a very hard time in discussing what an observer will see, because that observer will also be a string. How does a string experience the presence of other strings? How does all this work? These questions are very difficult to pose, and it's much more convenient to solve equations without trying to answer such difficult questions. But I think the questions in this case are extremely important to understand how to answer them. So one person who gave a definite, very interesting, very unique contribution was a guy at the center of this picture, who most of you will know as Stephen Hawking. You'll also be somewhat surprised perhaps to see him together with Einstein and Newton, whom you also might recognize. But Stephen was very good in doing time warps, so he had no difficulty with the fact that Einstein was already dead and Newton was dead for several centuries before he came into this world. Now he can make a selfie of three together. This, of course, was an episode in Star Trek where Stephen had announced his interest of playing a role there, and so that's what happened. Anyway, stories to tell about that, but I have another talk to give, so I'll return to the black holes. So the main assumption that Stephen first made in trying to understand how do quantum particles behave in the background of a black hole, that should be a much easier question than the whole lot together. Just take a black hole, drop in a particle and see what happens. And then he found it very difficult to answer the question in a way that satisfies him. So then he asked a simpler question. What if you do not drop any particle in the black hole? The thing is in a pure vacuum. Then what happens? Then how do the quantum fields of these particles fluctuate? Even that question turned out to be very hard because it looked as if he was unable to define empty space near the black hole. So he thought he was in deep trouble. He didn't understand things. He was actually landing into one of the first paradoxes of black holes. And when a theoretical physicist like me, and also like Hawking, of course, when they encounter a paradox, they jump in the air and say, this is great, we are going to solve this paradox. Maybe we'll learn something new. And yes, Stephen indeed learned something new. He learned that an infalling observer into a black hole, maybe that observer will see no particles around him. We can sort of postulate as an initial state for Einstein's equations. But then another observer who stays outside the horizon will not see the vacuum state, but will actually see particles. And at first, Stephen thought he was making a mistake. This can't be true. This is just wrong. I mean, the vacuum should be the same thing for all observers. This wasn't the case. So what he found instead was that you have to look very carefully at the different ways in which the different observers consider the notion of time. That is, of course, the starting point. When you take any quantity as a function of time, you can take the wave function of that quantity and then Fourier transform it in the time direction. Then you get a function as a function of frequencies. And that function is related to energy. So the notion of energy is strongly related to the notion of time. And now here we see the interesting thing of two observers of a black hole, one observer outside and one observer going through the horizon of a black hole. In this picture, this is a well-known Penrose diagram, which many of you must have seen before. In the Penrose diagram, you contract and expand space and time any way you like, except to make sure that in this description, in this diagram of the universe, all light cones take the same position. They are 45 degrees and they're pointing upwards. That's the only constraint. And then you can draw the entire universe in such a diagram. So this is matter which contracts and makes a black hole. Then this line of 45 degrees is a horizon. But this is the last point where you can sit such that you can return to outer space, which is this square here. But if once you're inside this red line, you're lost. You're hit by this black hole singularity. And the question is, what does an observer falling in then see? Now the observer here, at this point, which is blown up in this picture here, the observer experiences time very differently from the outside observer. For the outside observer, these blue lines are lines of equal time. For the observer here, those are not at all the lines of equal time. They are like these red lines. They are lines of equal time for this observer here. So totally different. And even more so, once the observer crosses the horizon and once he tries to describe what happens in this domain, you'll see the time here runs backwards. These lines just continue, so time runs backwards here, forward here. If you're a good mathematical physicist, you realize what is happening here. the equal timelines for the distant observer show to you how it happens with a time boost. If you go one step forward, you see the same black hole. The black hole is basically invariant under the evolution of time. But here, at this spot, it is invariant under the rotation of these lines, and these rotations can be recognized as Lorentz transformations. The Lorentz transformation does something with equal time coincidence, so the equal time line is like this, or after a Lorentz transformation is like that, after another Lorentz transformation is like this, and so on. So these are the Lorentz transformations, and of course nature is also invariant under Lorentz transformations. So what is invariance under a time boost for a distant observer is invariance under Lorentz transformations for the local observer. And now we can say, oh, but that's nice. If you want to know the vacuum state is also invariant under Lorentz transformations. Therefore, this observer will continue to see the vacuum, and that is a relevant, a valid solution to Einstein's equations. But this vacuum does not coincide with the vacuum of the distant observer, because they both experience the notion of time differently. Because they experience time differently, they experience also frequencies differently. And frequency has to do with energy. So these two observers have a totally different opinion about what energy means. When you have a different opinion about energy, you'll have a different opinion about creation or annihilation of energy. And the vacuum is defined by the state out of which you cannot get any further energy. So to annihilate energy out of the vacuum is impossible. Therefore, the energy annihilation operator should give 0 on the vacuum. But that operator now depends who you are. Are you falling into a black hole? Your operator that reduces the energy is different from the operator that an outside observer sees. And therefore, the outside observer has a different opinion about the vacuum state than the local observer falls in. That is the fundamental ingredient that went into Hawking's discovery, that if an infalling observer sees nothing, the outside observer sees particles. When he first arrived at, Hawking's conclusion was, well, I made a mistake somewhere, this is nonsense, this is wrong. But when he couldn't correct his mistake, he asked the next question, what kind of particles are they that I'm seeing? And then he found out that a black hole behaves like a thermal object. And these particles just come out thermally, as if it is evaporating. And then he said, oh, of course the black hole evaporates. This actually had been proposed earlier by an Israeli physicist, Bekenstein. But now Hawking realized how he could actually compute this effect. Bekenstein could not compute the actual temperature of a black hole, but now Hawking could, because he had done these calculations. It's a marvelous calculation. It's doable. You have to have some patience, but I checked the whole calculation because I wanted to know what's wrong with it, because there's something that didn't make any sense. What Hartle and Hawking found was that if you have a situation like this, and if the local observer sees a vacuum, the distant observer sees an excited state. What kind of excited state is that? Well, there's a region 1 here and a region 2 here. Region 2 is diametrically opposite to region 1, where time runs in the negative direction. If you understand what I mean, well, probably you don't, but it's difficult to imagine what it means that time runs in negative direction. But hold on for a moment. Then in region 1 there are particles with energy E and other quantum numbers n. In region 2 there are particles with the same energy E but going backwards in time and the same quantum numbers n. And then you have this entangled state. The two particles in 1 and 2 must have the same energies, and they come with a Boltzmann factor e to the minus 1/2 beta E, where beta is the inverse temperature. That will be the Hawking temperature. The 1/2 is needed because to get the amplitudes themselves, to get the probabilities out of the amplitudes, you have to square the amplitudes. So when you square the amplitudes, this 1/2 disappears. And then you get a Boltzmann factor for things at finite temperature. This temperature beta was totally fixed by the mathematics of this situation. And what we see is these two particles are entangled. The fact that they have the same energy is very nicely explained by saying that this is invariant under Lorentz transformations. But under a Lorentz transformation is a generator which has as a generator the energy in region 1 minus the energy in region 2. That's because time runs forward here and backwards here. So Lorentz transformations generate, have a positive contribution of energy here, negative contribution of energy here. If the energy here is equal to the energy here, then the whole thing is invariant under Lorentz transformations. And that's our first starting point. What the local observer sees as vacuum is invariant on the Lorentz transformations. Well, exactly this state is invariant on the Lorentz transformations. So that turned out to be the first ingredient to an answer as to what's going on with particles visiting the horizon of a black hole. It's beautiful mathematics and also beautiful physics. A black hole seems to behave like a light bulb. But there was a problem with those light bulbs. And well, there are various problems with the light bulb. One is that time runs backwards here. What does it really mean? And how do you write the thing beyond thermodynamics? Because in most branches of physics, thermodynamics is what you do if you apply statistics. The problem is too complex to treat in all with only exact Schrödinger equations. So instead, you take an ensemble of systems or wave functions onto which you apply Schrödinger equations. And if you do the ensemble just right, you get a thermal situation. But at the same time, you say, well, this is because we can't control everything. We do statistics. But in principle, the system is described by a pure Schrödinger equation. So we don't have to take the statistical average. Things might be not in thermal equilibrium, but in some other equilibrium or not equilibrium at all. We want to be able to derive physically, mathematically, what happens under such circumstances. So the next thing people said, including Hawking in the beginning, was what are the fundamental equations before I did thermodynamics to the black hole? And now comes a big sort of counter-climax. We did not succeed in writing down what happened before you made this thermal ensemble, as if black holes have to be thermal. And that was Hawking's later conclusion. Black holes have to be thermal. You can't single out a single state without being punished some way or other. And so, black holes, for that reason, misbehave somewhat. They don't have themselves controlled by a Schrödinger equation, as Schrödinger would have wanted it, and as most physicists, particularly particle physicists such as myself, wanted it to be. So there's some very mysterious problem, and this problem has got a lot of attention. It's a very important problem, the problem of what does a black hole do with the information that falls into it. Because that's really the bottom line of the whole situation, that we are losing track of the information of things going in, and the only way we can handle that situation is by doing statistics. We can say every single state might emerge, so we just do statistics, and then we do thermodynamics, and then we can calculate what happens. Fine, but we want to know more precisely what happens by writing pure quantum mechanics. How does that go? That was now a fundamental question, which is totally unanswered by the answers we had so far. So this difficulty might eventually force us to look at space-time itself in a different way. And this is why I find this topic so highly interesting, that it tells you something quite unexpectedly about space-time itself. And the way I think one can have a handle on the behavior of a black hole is to ask a question just like the question Hawking asked, which is take the background configuration, take the configuration of a black hole as a background, allow particles to move in that background, and make some constraint on what kind of particles you do allow, and ask how that situation evolves in time. Shouldn't we this way be able to write down pure quantum states? So if we go backwards for a moment, you see in this picture, this red line is a so-called Cauchy surface. The Cauchy surface is defined to be a space-like section, three-dimensional section of four-dimensional space-time, such that when you define all particles in that space-like section, basically you define all particles at one instant in time. All particles, or perhaps also their velocities, but nothing more than that, just their positions, their velocities, and you take that for all particles, and now you press the button, switch on the laws of nature, to see how the situation evolves to the future. And that should be a well-defined problem. It should be a well-defined problem here. We take the background metric of a black hole. We know how to formulate all the field equations of all the particles that are relevant in that domain. Shouldn't we be able to solve those field equations and then find out how the system evolves during the entire lifetime of the black hole? And shouldn't that deliver us the pure states that we want to describe? The answer is no, it's not going to be that easy for various reasons. And that is that as time goes on for the distant observer, the local observer here performs Lorentz transformations. But you only have to make a few elementary time steps here, which is not very much. The unit of time is maybe a millisecond for even a large black hole, or a microsecond for a black hole of the order of the solar mass. So after a couple of microseconds, you made a tremendous amount of Lorentz transformations here, an enormously big Lorentz boost. The Lorentz boost is so big that even if you take very moderately behaved particles here, particles moving very slowly, slowly compared to the speed of light, so slowly enough to make their energy and momentum negligible quantities in Einstein's equations, very soon, after time goes on, these particles will have been boosted to such high Lorentz transformed velocities that they will disturb the metric in a big way. In fact, in a fantastically big way, which I'll try to explain. So something goes terribly wrong if you follow this program the way you would like to follow it by looking at the books. You cannot do ordinary particles in the background of a black hole without taking into account the fact that they will back react. These particles will become so energetic that they'll generate gravitational fields, and these gravitational fields are going to throw the whole problem wide open again. Something is completely wrong with the picture that we have today. And so how do you do it correctly? Now my claim is one can do it correctly. One can consider the Hilbert space spanned by all low energy particles in the black hole background, and we can do that without making a call upon string theory to tell us what happens. I don't need the ADS-CFT, I don't need the de Sitter spaces, and I don't need extreme black holes. I want to describe the most elementary prototype of a black hole, the Schwarzschild black hole itself, the one proposed, found by Schwarzschild shortly after Einstein wrote down his theory of general relativity. Schwarzschild found the spherically symmetric solution. He said, well, what about this solution then? And Einstein said, it can't be right, because there's a singularity and something is very wrong about that solution. So that made the solution very interesting as a black hole. So, so when string theorists considered for the first time black holes, their first reply was, we got it all solved. Right? Don't work any further. We have a solution, a stack of D branes and so on, and the solution consists of pure quantum states, so you solve that one on the side, and you don't have to think any further. We have the solution. But that solution does not tell us what happens when an observer enters into a black hole. It doesn't tell us in what way this thing obeys Einstein's equations as a background. So although the general idea seems to be of the right kind, string theories also produce the thermal behavior for these black holes as if they got it all under control, but I claim they have not. And that showed a couple of years ago when these four people, Almeri, Marov, Polshinsky, and Sully, just discovered that there's something very wrong with the black holes that they were considering. And that is that there were difficulties with precisely the entanglement of the particles which are opposite to each other in this, around this horizon, and the no cloning theories, the fact that you can't make a double image of a quantum particle in space-time. If you try to clone a particle, you get a situation which doesn't obey the proper Schrödinger equations. Can't be right. So there were some deep problems, and the only way to get around these deep problems was that what they predicted was that at the horizon of a black hole, space and time are not that clean and beautiful at all. There is what they call a firewall. A firewall means that when you try to enter a black hole, you will not see this vacuum state at all, as Hawking assumed. In contrast, you will feel a shower of infinitely energetic particles. Those infinitely energetic particles will kill you, so you will not be able to get through the horizon at all. That was their preliminary answer, but of course that can't be right, because that is directly in conflict with the basic tenets of Einstein's theory, that you should have observers, and what kind of coordinates you use should be irrelevant, so whether or not there's a horizon depends on long distance effects, which shouldn't affect the local physics at all. So there must be something very wrong about the firewalls. So the next events that happened, and lots of people wrote papers why firewalls are wrong. But it's not that easy, because if you look more carefully, you find, yes, as soon as you consider a black hole in a pure state, then that pure state is by definition not the Hartle-Hawkins state, it is something else. If that situation is something else, then the local observer will see particles coming out. But those particles coming out will form an infinitely dense curtain just at the horizon, because there will be an infinity of particles coming out at the horizon. How do you get around this problem? And so people were too quick, I believe, in giving their answers, whereas you have to think more carefully about what is it that's really going on. So we have to do something to improve our theories. And the first observation is we were too simple in applying the theories that we know today. We have to take into effect some things which are absolutely essential. And the first thing which I now advocate is what we have to do is remember that ingoing particles in a black hole and the outgoing particles, which Hawking predicted, and to believe that that prediction was basically correct, these ingoing particles and outgoing particles will mutually interact. Well, but we are familiar with mutual interactions of particles in quantum field theories. We also assume that these are small perturbations. So when we want to have the entire Hilbert space, we do as if these particles don't interact at all, and then we introduce as an afterthought that particles interact a little bit, and then we do perturbation expansion, and everything is fine. That's the way quantum field theories work. But this isn't an ordinary quantum field theory. This is quantum gravity. And there's a problem with gravity, which is that the gravitational forces are not confined. They are not renormalizable. You can't write a good theory for them. In particular, when particles start to move very fast, the gravitational force becomes extremely strong. Far stronger than allowed if you want to do perturbation expansion. So to treat the gravitational interaction between ingoing particles and outgoing particles is illegal. As soon as these particles are coming very close together at the horizon, well, there's an infinite shower of particles at the horizon, so there will be many of them very close hitting, of ingoing particles hitting the late outgoing particles. That will be catastrophic, and that will just spoil all your equations. So the only other thing you can try to do is take that effect into account from the very beginning. And so the bottom line there of that is you cannot ignore the firewalls that you get this way if you want to describe the pure quantum states. You have to do something better. And the gravitational force diverges tremendously on the horizon, so it becomes a strong force, a super, hyper strong force that you cannot possibly ignore. So, but then you say, okay, then we have to include that force right from the beginning as a kind of new boundary condition. It will have a big effect on the whole idea of black holes. Let's start again from fresh. And that is possible, and then you discover one nice thing about this force. It's hopeless. These firewalls seem to destroy everything you thought you knew about black holes. But there's also something very nice about the firewalls. They are linear. You're allowed to superimpose firewall particles without changing the equations. So the equations for the firewall are linear. And they say, maybe I can do something. When the equations are linear, we can try to find new expressions, new equations that one has to obey. And yes, you can superimpose the equations, and that gives you a very interesting new behavior. When equations are linear, in a spherically symmetric environment such as the Schwarzschild black hole, then a sort of Pavlov response of physicists should be, then we expand everything into spherical harmonics. So when some time ago Hawking gave a talk here that he had found a new solution to this problem, then my first reaction was, I can do it better, because he seems to be ignoring this gravitational interaction. I know how to do it. And then I decided, well, let's try to solve the equations. How do you solve equations which are linear and they act on a sphere? You expand in spherical harmonics. Of course you do. So I took all my variables, expanded in spherical harmonics, and found beautiful, simple equations that any undergraduate student can solve, with perhaps some guidance, but that's just because they're undergraduates. But otherwise, they should be able to solve the equations. It's not hard. the equations are low-dimensional equations, so nothing about functional integrals or something. So you can hardly go wrong. And that makes the problem extremely interesting, because here we have equations, they can't go wrong, but something does go wrong. So these firewalls, we should do something to remove them. What do you have to do? And the answer to that is mind-boggling, I think. The answer that it works perfectly if I modify space-time the black hole. Then you say, that should not be allowed, because Einstein's equations tell you everything. Einstein's equations do not tell you everything. They don't tell you what the boundary equations of the boundary conditions of the solution are. And in particular, you have a freedom that nobody, well, not quite nobody, most people don't use. Actually, the freedom was used by some people in the 1980s. That is Whiting and Norma Sanchez, Bernard Whiting and Norma Sanchez. They briefly considered the possibility that you have to identify points. So there's, when you have a black hole, you find that in the most extendable coordinates you can use for a black hole are the so-called Kruskal-Szekeres coordinates. And in these coordinates you find that every point in our universe is represented twice in the space-time. So when you extend the Schwarzschild solution for the black hole, you find that every point in our universe is represented twice. And people just accept that, and they say, okay, interesting things happen here, and there's another black hole, the replica of the one you're looking at, sitting somewhere else in some other universe, where also interactions take place, and if something happens here, something else happens there. Unfortunately, that picture doesn't work, so you have to do something else. And the thing I want to advocate is the only other resolution to this problem is to say those points are not two different points. It can't be. You have to identify them. The question is, how do I identify which points here do I identify which point there? You have some freedom in this option, but not much. There's exactly one choice which is physically completely acceptable, except you don't see it when you do the classical calculation. Classically, you don't see it because you're talking about physics behind the horizon. And nobody can ever make an observation of what happens behind the horizon. So it's a physically an empty statement that I can make. Well, yes, for the classical black hole, it's empty, but for the quantum black hole, it is not. For the quantum black hole, it's crucial. And I'll try to explain that, which I call antipodal identification. On the horizon, you can have one point, and you can look at the antipolar point, and you have to identify them. In mathematics, this is well known. This replaces an S2 sphere by an S2 projective sphere, where you have the sphere formed by lines, of which the antipolar points are, by definition, are identifying the same line. So the antipolar points are identified. Then that gives you an identification of all the other points in this metric. And that is a new space-time metric, which obeys all the same Einstein equations, generates no singularities in the physical domain, and nobody can tell me why that shouldn't be a legal solution, except you have to say how it got started. So we'll leave that to the end of the talk. How can such a solution come into being when a black hole is formed? That's a very difficult question, but I think the question can be answered. Now, these are 3 points, and I think those 3 points are extremely important. And most publications I see in the subject, they ignore all 3 of them, or at least one of the 3 points, and then I know that you're making mistakes. So you have to take all these 3 points into consideration. Now, how do we take into account the gravitational interaction between ingoing and outgoing particles? In principle, it's very easy. All you have to know is how does a very fast-moving particles interact gravitationally. Well, you get a very fast-moving particle by taking an ordinary particle, standing still, and just boost it. We know how to perform Lorentz transformations in Einstein's theory of general relativity, no problem. So let's do that. We take a stationary particle, standing still like this, obeying the Schwarzschild equations for its metric. So this is the Schwarzschild particle. And now I just boost the Schwarzschild particle to as high a velocity as I can. Such a way that I let this mass go to 0 while this boost parameter goes to infinity, in such a way that momentum stays finite and large, energy stays finite and large, energy and momentum are basically equal when the thing moves with the speed of light. So that's easy. And then what you find is a very interesting solution to Einstein's equations, a new one, between quotation marks. It's nothing else but the Lorentz transformed familiar Schwarzschild metric. But this Lorentz transform metric has flat space behind it, has flat space-time in front of it, only where you glue this flat space-time onto that space-time on a transverse plane, and on a transverse plane you make a mismatch. You shift them in a way that depends on where you are. That means that you generate curvature on this line, on this surface, this flat surface here, which divides future from past. How that curvature goes is completely prescribed by this solution of the stationary black hole. So this is an elementary exercise, in principle anybody can do. It's a bit hard to do it without mistakes, but this is the outcome, that it looks as if when a very fast particle moves this way, another particle is being passed by this plane. The ways these two spaces are glued together is twisted, has a mismatch. So a particle goes through, but then appears at the other end shifted. This shift is a shift of its coordinate u minus. It's a shift in the light cone minus direction. Same thing as we're saying that the particle itself moves in the light cone minus direction here. So this green thing moves in the light cone plus direction, but then it gets shifted by delta u minus. And delta u minus is simply proportional to p minus, the momentum of this particle. So the bigger that momentum, the bigger this shift. It's a linear relationship. Furthermore, this relationship is such that delta u minus depends on the transverse distance. So when they're further away, the shift is smaller than when they're very close together. It's actually a logarithm, so there's an ultraviolet and an infrared disease of this logarithm, but those are very minor diseases, very slow and present in practice. So, but this logarithmic dependence tells you that there's no way to choose your coordinates such that this whole effect vanishes. You can make it vanish at one point. You can make the first derivative vanish at one point by performing Lorentz transformations. But you cannot get rid of the effect entirely because a logarithm is a non-trivial function. This logarithm is also a Green's function in 2 dimensions. Remember, if you write down the Laplace equation in 2 dimensions, then in 2 dimensions the solution is not 1 over x or 1 over x squared, but it is log x. So the log x is a Green's function in 2 dimensions. Of course it is, because this plane that had the particles that divided the front from the back on these 2 flat spaces, this plane is a 2-dimensional plane. So on that plane, all these functional dependencies are solved by 2-dimensional differential equations, and the outcome of that is a logarithm. That's easy. So you could have guessed a logarithm. You could have guessed that the delta u minus will be proportional to p minus. The only thing you could not have guessed is the -4. So the -4 is the most difficult part of this whole expression. This comes out of a hard calculation. So what does it do to black holes? And now comes the interesting part. Imagine a fast particle getting into the horizon of the black hole, but I look at this in particle after some time. After some time, it seems like going into the black hole very close to the past event horizon. Since I'm looking at later times, this ingoing particle seems to have moved far to the past, very close to the past event horizon. But also its momentum has become very large. So this particle has become a particle with tremendously big momentum, and so all the other particles, the Hawking particles, which are supposed to give this Hawking vacuum state, they are being dragged along by the same amount here for all these particles. This amount is called delta U, and the delta U is the same everywhere. And so this is an important effect. And this Hawking particle is being shifted in this direction. This green particle came out from the opposite direction, moved into region 2. But since time runs backwards, the green particle moves like this. Now, what does a particle do when it sits here? When it sits here, the drag effect drags it across the horizon, and then where does it go? You might have thought it goes in this direction. That is a mistake. And when I first did the calculation here, I let this particle go in this direction, and then I realized immediately this is wrong, because this is not what the local observer will see. So what am I doing wrong here? I thought, okay, I throw my calculation away, it's wrong. But then I took it back out of the wastebasket and said, it doesn't look so wrong. It gives me something also very right. If this were a Cauchy surface, this past horizon, of outgoing particles, then all outgoing particles seem to be shifted. And whether they later will be carried forward in time because it's in region 1, or backward in time because it's in region 2, that's of later concern. So the Cauchy surface survives this Shapiro shift effect. And that is so interesting. You see, this way we can make a Schrödinger equation for a black hole that obeys unitarity, because it conserves all the information. Particles either are moved around just a little bit like this. This particle here is not removed from the spectrum altogether. That would be loss of information, not allowed when you do unitary quantum mechanics. So the only solution is that when it's shifted, it comes out back in this direction. And now, in spite of the fact that it looks like the wrong thing to say, because a local observer doesn't see such a thing, you can say yes, but from the point of view of a Cauchy surface and of equations for particles moving in the background metric, this is the only equation that ensures that the behavior will be unitary. So I must accept it if I want a unitary equation. So the question now is, what is the price I'm going to pay? And that's a very interesting question. So we start with the familiar looking expression for the Schwarzschild metric. Many of you know this expression here. The 2gm over r is basically the gravitational potential, but it occurs in the space direction as well as in the time direction. This component here describes order of gravity. This here describes that also space is curved, not only time but also space. And omega stands for the two angles on the horizon, theta and phi. D omega stands for d theta and d phi. Now I'm going to live up to my promise that I'll say I'm going to consider first soft particles on this metric. So I'm not going to consider these very hard particles which are accumulating on the past event horizon, or the future particles which accumulate on the future event horizon to come out much later as soft Hawking particles. But while the time these particles accumulate on the horizon, they're very hard particles. I can't take them into account. They should not be part of my Hilbert space. In my Hilbert space, I only see the things that live on my Cauchy surface, which are all relatively soft particles. Let's keep that. Let's see what that brings us then. So soft particles, by definition, are particles whose momenta are low compared to the Planck energy. Hard particles have much bigger effects, have much bigger momenta. Therefore, the hard particles have an effect on the metric. But these hard particles are only accumulating on the horizon. So they seem to do very little directly on this Cauchy surface. So let's begin by leaving the hard particles out, remembering that actually nobody ever saw a hard particle. We have never detected in the cosmic rays particles whose energies are beyond the Planck energy. You know, we've detected tremendously energetic particles, but no particles with energy beyond the Planck energy. Maybe there's some law of physics saying, leave those out for a moment. And that's what I'm going to do, leave those out for a moment. Later we'll be concerned about what we do wrong by leaving them out completely. And from that moment on, we say now we're going to use other coordinates, the tortoise coordinates, by saying these are the equations for radially moving and outmoving particles. These will be the equations for local light cones. So I'm going to replace the r and t coordinates of a black hole by light cone-like coordinates close to the horizon, where r is nearly equal to 2m, but not quite. Then you have this light cone picture. What you see here is actually more like an artist's impression of a black hole, where time runs forward, and you can still see that the black hole is basically stationary in time. Then the singularity seems like living in the center. But many people got that wrong when they write popular stories of the black hole. There is no singularity in the center of the black hole, because this singularity is not simultaneous with the other physics you're doing here. This singularity lies in the infinite future. Even though it sits at the center of the black hole in these coordinates, you have to realize that all the light cones here are pointing in this direction and not in this direction. So the light cone for a particle that went through the horizon is forcing particles into the future singularity. So singularity is space-like, not time-like. It's a very important thing to realize. Now, we first want to understand what happens during a short time interval. And a short time interval is a time interval that is so short that light takes is about this amount of time that light takes to to cross the Schwarzschild metric classically. So it's of the order 2gm in Planck units, or 2m Planck units. That's about the length of this time interval. During this time interval, the particles were being Lorentz boosted, but only by relatively small gamma factors, so not yet enough to make them really hard particles. Most particles will stay beautifully behaved when you consider just this short time interval. Very important. Now, the generic black hole state, and this is now an assumption, that the generic black hole state is now described as a metric for an eternal black hole with only soft particles in it. Why eternal black hole? Well, I am not considering the formation process or the final evaporation process. I'm leaving out those particles. So the only black hole that has that is the eternal one. So now I describe the black hole metric as an eternal metric. And the advantage of that is that this is the maximal extended solution of the equations. So there you can play the most tricks of, to see how particles and particle state behave and how the Cauchy surface evolves in time. So it's a very important thing to do. And now, physically, what happens is the following thing. If you send in one extra particle into this black hole, that's this line here, then all the outgoing particles are being shifted a little bit. Most of these shifts are not very significant. They're very small and they don't change much the state these particles are in. But there's one particle which is being shifted in a more elementary sense. Look at the red blob here. This particle is coming out first, but now sending something in, sends this particle back into the horizon. So now something more elementary happens, and no matter how weak this particle was, this thing will sooner or later happen. So we better take it into account. And that's now the, this is just text I've been saying now. The ingoing particles will leave their footprints in the outgoing particles. The footprint is that the outgoing particles, whatever pattern they came out in before you sent in this particle, after you send in the particle, the pattern changes. The pattern is being shifted. So the momentum of the ingoing particle generates a shift in the outgoing particles. Very important to remember. And this is the Penrose diagram of the eternal black hole, and these are now the shifts brought about by this ingoing particle. And I see that that what I'll first do is I ignore this ingoing particle, but I can also say this shift is a footprint that the outgoing particles have, the ingoing particles have in the outgoing particles. Now, this footprint can be considered, can be made anything. If I choose the ingoing spectrum sufficiently generic, then I can make these outgoing particles sit anywhere where I like it. So I can modify the state of outgoing particles any way I like by sending in particles. So instead of saying what these very energetic particles are going in, I can say where are the outgoing particles. And now I can say I'm not going to do double counting of quantum states. I'm going to forbid quantum cloning. So I'm not going to say what are the ingoing particles and what are the ensuing positions of the outgoing particles, because then I'm counting degrees of freedom twice. So what I do now is I take the ingoing particles, and as soon as I know what the effect on the outgoing particles is, I say that those outgoing particles take the position of the ingoing particles. Their footprints will remind us of what the ingoing particles were, and by replacing the ingoing particle by the footprints they leave in the outgoing particles, I've made a unitary transformation. So this is going to be the transformation that generates a unitary evolution operator. And then you have to say, but wait a minute, what about these spherical harmonics? Well, we are going to do this in a spherical harmonic environment. We consider the ingoing particles, the momentum distribution of the ingoing particles as replaced by expansion in spherical harmonics. Then also the displacement of the outgoing particles are generated by the same spherical harmonics. And that's the nice thing about the Laplace equation on the horizon, that if you have one particular spherical mode with an L and an M, then the solution to the equation will again be in the same spherical mode. So this logarithm, which I told you about before, is just a factor, 1 over L squared plus L plus 1, on the horizon. And that means that if I take the spherical harmonics for the positions of the outgoing particles, they are related to the momentum spherical harmonics of the ingoing particles, but this relation is a separate relation for all Lm values. So the different Lm values don't crosstalk at all. And that makes the equation so simple. I can now look at one L and one M and look at the equations. And the equations are extremely simple. All you have is a U plus or minus. Those are the positions on the event horizons. And P plus or minus, which are the momenta on these horizons. And the way they evolve under Lorentz transformations is that the U's will scale with e to the minus tau, and the momenta P will scale with e to the plus tau as time goes on. So, so basically the math becomes relatively simple. So now we say, but there's something about inflow and outgoing particles which is unfamiliar. And that is the coordinates we use. If we would replace the U and plus and U minus coordinates, both the position of a particle on the horizon, if we would replace it by an exponent, so replace U by e to the power rho, where rho is now the new coordinates, then I have a degree of freedom which doesn't blow up exponentially in time, but just linearly in time. This rho just increases linearly in time because it sits in the exponent here. And same for in and for out. However, if I write U plus is e to the power rho plus, then I have to remember that E plus can still have both signs. It can be in region 1 or in region 2. Therefore, I must put a sign in front. The sign doesn't want to be exponentiated. So U plus is plus or minus e to the rho in. The outgoing particles are plus or minus e to the power a new coordinate rho out. And these rho's now obey much simpler equations than the original U plus and U minus. So that helps a lot. If you use these so-called tortoise coordinates, these are coordinates which come closer and closer and closer to the horizon, but never reach the horizon, because it's an exponential. So it goes at e to the minus tau, it comes closer and closer to the horizon. But you can write down plane waves in terms of these coordinates, and the plane waves just move to the left eternally. They never reach the horizon. That's a famous statement that an observer who goes through the horizon, for the outside observers, never really goes through the horizon. They just get stuck there and stop. So that's the fundamental equation. You can do this for the ingoing particles and for the outgoing particles which go in the other way. I'm running a little bit short of time, so I don't know how much time I would have. Okay. So now comes the interesting thing about X being conjugated to P, because positions and momenta are, of course, each other's quantum conjugate. Here, quantum mechanics comes in very directly, because I was considering positions of particles on the horizon, and I was considering momentum of the particle on the horizon. You say, aha, momenta and positions are related by very simple commutators. So this X state and the P state have inner products which are this simple, e to the IPX. And now comes with the spherical harmonic expansion, I only have to look at one U and one P, and of course they obey this property with the square root of 2 pi, because there's only one dimension I'm looking at. When I Fourier transform the function in X, I get a function in P. That's what this basically says. But now I do it for these tortoise coordinates, and I get inside here these two signs, the sign of sigma and the sign of P, multiplied together, and e to the power rho X and rho P, but now in the exponents, so I get double exponents. These equations look rather horrible, but this is the integration kernel for the Fourier transform to replace the ingoing particle by its footprint in the outgoing particles. And this is now an exponential behaving function. So this is the exponential of sine of X, but when the X is exponentiated, so starts out very slowly at the left, but then starts to oscillate very, very wildly here. So wildly that very soon you can say, well, further oscillations will be invisible, so I remove them. If you say that, then this function will get a compact or nearly compact support. So we now get integral equations which become very interesting. And to illustrate this, if you have a Fourier transform of function of X, you have to realize that the Fourier transform peaks where the momentum P times the relevant positions X are of the order 1. So if X dot P is of order 1, that's where the Fourier transform of a function tends to peak. But far away from this, the Fourier transform is very small in all directions. So this means that rho of X and rho of P together like to be approximately 0. So this is how an ingoing particle changes into an outgoing particle. For the ingoing particle, the rho has the opposite sign as for the outgoing particle. And this is how the gravitational footprint of ingoing particles can be given onto outgoing particles is this property of the commutator of x and p. So I do this, and then I'll skip some of the calculations because now I got some equations on my screen. And the equation is that what I have is a wave function in region 1, or the wave function can be in region 2. So the wave function now is a doublet. Half of it sits in region 1, the other half sits in region 2, like a spin 1/2 particle. And now I can plug in the equations and I find that the outgoing particles are the footprints of the ingoing particles. And the matrix I get is this matrix where this kappa is some phase. And kappa is the energy, but these are not phases, sorry. These are just, they generate hyperbolic sines and cosines. The fact that this equation is unitary is a very interesting consequence of this property of the Euler gamma function. This is the Euler gamma function. It's what you get if you do this undergraduate exercise of integrating these exponential functions. You get the gamma function. And the gamma function has this property that if I put a 1/2 here, you expect normally a sine, but if I have a 1/2 here, because you get the cosine, the absolute value square of the gamma is pi over cosine hyperbolic pi kappa. And that cosine hyperbolic is precisely what you need to make this matrix a unitary matrix. So this comes out as a unitary scattering matrix. Finally, we have to put in these factors L squared plus L plus 1, which were the Green's functions for this shift. So for higher L, the shift occurs later than for low L. And this L occurs in the equation in this particular way, logarithmically in the exponent. So this is now my entire expression for the scattering matrix, and it is a unitary expression, saying that at every L and M, whatever goes in comes out with the same L and M sooner or later. It might come out centuries later, we don't know that, but eventually it will be a completely unitary transformation. And this matrix can be shortened by saying F plus, F plus, F minus, F minus, and this is the relation between F plus and F minus that guarantees unitarity. This is exactly what follows from these gamma function expressions that I had. So this black hole has two asymptotic regions. And therefore, although I got unitarity, everybody will say this is wrong, because you're describing two black holes, not one black hole. So something still has to be done about this region 1 and region 2. What is it? And the only solution I found was that region 2 has to refer to the antipode of region 1. Not region 1 itself, because then you get a singularity on the horizon of a kind that would be forbidden by Einstein, by Hawking, by everybody. So we shouldn't have that region 2 is region 1, but if you say I rotate 180 degrees and then I get region 1, then I get no singularity, and everything should behave perfectly fine. And this is what I mentioned, Sanchez and Whiting, who considered this already in the 80s. This is a crucial change in our picture of space and time. So instead of having space-time as one normally thinks, I say this diabolo would have been space-time without the identification. Now I say if you follow a path in space and you drop over the edge here, then you flip over to the other side and you continue past the path back in the physical space-time. So space-time has been divided in two by this procedure. But you have to do that. So I think a better way to rephrase Einstein's theory of general relativity is to say you can make all coordinate transformations, but make sure that one point here corresponds to one point here, not two, as we normally do in Schwarzschild extension with Kruskal and Sekeres. So only one. Then it works. But this has this very strange, what's that? LaTeX, I don't know what it is. This is if you remove half of space-time, and the picture one then gets of space-time itself is a little bit what I would call a vacuole, an empty spot in space and time. I take ordinary space-time, the blue region, and I excavate a hole out of that space-time. There's nothing in that hole, not even space-time itself. No particles, no space-time, no nothing. Just if you follow a trajectory that reaches this cross, you jump over to the other side and you get out here. If you follow a trajectory that reaches this figure, you jump over to the other side and continue here. This is a valid boundary condition that says that on the horizon, these antipolar points are identified. Away from the horizon, they are not identified, so you count still every point in space-time once independently. So this is a valid way of describing space and time if a black hole is there. Classical physicists will see no difference because the only change takes place behind the horizon. But for this quantum effect of the shift of the Cauchy surfaces, it is essential to have this picture. Little remark in red here that if you do this kind of thing, only the odd values of L will survive. M can still run from minus L to L, but L itself has to be odd. And that's because if you go from one side to the antipolar side, then the position on the horizon will shift sign. And also the momenta that you're considering will shift sign. So everything shifts sign if you make a rotation of 180 degrees. That happens if your spherical harmonic is only consists of the odd and L values. I don't know what to do with that. It's just one peculiar thing. And last, and then I should stop, is I can now make a new kind of Möbius strip. You know, you can make an ordered space-time, you can make a Möbius strip, very easy. You take a long band, you twist this by 180 degrees, and you glue them together. You have a Möbius strip. But now there's a new Möbius strip you can make, and that is, you don't twist it, but you twist it in the time direction. You replace time and minus time. Now you glue them together. What do you then get? Well, this is not something you can normally make in space-time, but you can make it here. This twist takes place inside the horizon of a black hole. And now you can just continue, and you get a time-like Möbius strip. So this shows that something happens to the topology of space-time, which is non-trivial. And therefore extremely interesting, I would think, for discussions also of quantum gravity. We're not dealing with ordinary space-time. You are dealing with space-time that allows you to twist things that you never have been able to twist before. And yeah, I think I should stop here. I want to say something about the discreteness of the black hole microstates. Because the way I handled things looks as if now the black hole microstates form a continuum. Because the particles can sit anywhere on the horizon. That's not right. But it isn't right. If you look more carefully, you find that there are constraints if you put the particle and its footstep, its footstep. If you take this particle and the footstep both to be near the intersection point of two horizons, then you have to realize that the two horizons are like non-commuting coordinates. And you get the same effect as when you describe the Hall effect of an electron. You get a discrete set of states. So the states are discrete, and you get a lot of them if you go to high L and high M values. So the verdict here is there must be a highest L value that's allowed. Physically, that's quite acceptable. Mathematically, it's still a problem where this high L value comes from. And that is a question I've not been able to answer. But you see that you get interesting new pictures of the black hole without ever really using string theory. I mentioned string theory, I didn't use it. I mentioned ADS-CFT, I didn't use it. So this is still doing ordinary physics, which I like most, because I believe Einstein's relativity theory, I believe quantum mechanics. I'm not so sure I believe string theory, I'm not so sure I believe ADS-CFT. So I leave those out. That's my preferred way of working. Then you get these results that by themselves I think are quite worth considering. Thank you.
Well, that's been an absolute tour de force, and thank you so much as well for saying so much about Stephen, who of course is very sadly missed. I'm sure the speaker will be around for a little while afterwards to answer questions informally. Perhaps this isn't the moment to do it now. So let's thank Professor Hooft once again for such an entertaining talk.